Hello, my name is Chang Guo. This is my image processing project. My topic is dynamic threshold-based edge detection. Nowadays, edge detection is widely used. A large number of vision applications like matching and tracking use edges and lines as primitives. The common challenge of good edge detection algorithms is to have a low probability of error, failing to mark edges or falsely marking non-edges with the marked points as close as possible to the center of true edge. Considering the assumption that objects in an image can be distinguished on the basis of their gray levels, image thresholding technique is being used to determine the various regions into which the image can be segmented. And this new method using dynamic threshold is very good. In this method, the gray level image is thus to use multi-level thresholding instead of bi-level thresholding. Through this dynamic threshold-based edge detection, we part the image into several regions. And this is its main idea. It contains three aspects. First one is to compute the number of prominent peaks of image, and the second is compute optimal thresholds of the M-level gray level image. The third is detect edge using morphological operation. Now let's look at the first one. To get number of peaks, there need to be some steps. We need to compute set S0, S1, S2, and S3. For set S0, element is Fi, where I is the gray level and Fi is the corresponding frequency to the I's gray level. For set S1, it includes the elements representing the points of local maxima in the histogram. If Fi larger than Fi minus 1 and Fi larger than Fi plus 1, it should be put into S1. For S2, it removes unuseful element according to experience. The frequency of each element in S2 is 1% higher than the maximum frequency Fmax in the set F. This 1% is an empirical value, resulting from many times experiments computing the various gradual intensity changes from 2 level to 9 level. For set 3, it removed the elements having close peaks from set S2. Here we check the distance between gray levels of two elements in S2. If the distance is less than 20, then the element with lower frequency will be removed. Also, this number 20 is an empirical value based on experiments. After computing S3, we can get the number of peaks. It equals to number of the elements in S3. The second step, compute optimal thresholds of the M-level grayscale image. This is the multi-level threshold algorithm. First, we need to get the frequency histogram of the image. For each gray level I, the probability distribution is Pi. It equals to Fi multiply n, where n is the total pixels of image and Fi is the frequency of I's gray level. Second, for M level thresholds, we divide L, the total number of gray levels, into M classes as C1, 1 to T1, C2, T1 to T2, and Cm, Tm minus 1 to L. The total thresholds equals to M minus 1. M is equal to n, the number of the prominent peaks. Third, we compute Wk and Uk for each class K. This is the formula. Then we compute the variance sigma b. Where the UT is the sum of WK multiply UK. Finally, we got the optimal thresholds like this. This formula means the T, which T lets the augment B could be the max level. The optimal thresholds are calculated by maximizing the class separation while minimizing the areas of the classes as per the approach taken by Otsu's method of adaptation thresholds to select the most optimum threshold value. If the number of threshold classes is less than the number of peaks in the histogram of the image, the details of gradual intensity changes which are significant are lost, and if the number of threshold classes is larger than the number of peaks, there will be noise in the image. So, the optimal number of thresholds is equal to the number of the peaks of the image. The output is that. The next step, we start the edge detection. Here we use mathematical morphology to detect image edge. Although the basic operations are simple, the operations and their variance can be concatenated to produce much more complex effects. Generally, morphological image processing operates by passing a structure element over the image in an activity similar to convolution. This is the structure element. It can be 1, 0, or -1. And this is the detector. We use simple standard definition of all the morphological operators. To detect the edge, we use morphological operation of erosion. The set of difference between the original object and the eroded object produces a counter that straddles the inside of the counter of the original object. So the inside counter of the threshold image is the edge detector. We can compute it like this. And this symbol stands for morphological erosion operation. Then we do boundary thinning and remove the noisy pixels. The result of the edge detection last step is a boundary extracted image, which can be 2 or more pixel thick image. It needs to be thinner. Here we can use hit and miss transform or morphological transform to get extra pixels in each detection. If we use hit and miss transform, we could use masks from 3 masks. We can search extra pixels in the horizontal direction by rotating these masks by 90 degrees. We can get the mask for vertical direction, and by rotating these masks by 45 degrees, we can get the masks for diagonal direction. Using these masks, we compute the hit and miss transform of the image and remove the pixels searched by these masks. Also, we can directly use morphological function in MATLAB to implement the thinning operation directly and remove noisy pixels. The result of edge detection may contain a lot of noise, which have negative effect for normal utility. Kinds of methods can eliminate noise efficiently. Here we use median filter. That is the main steps.